Hello and welcome to the course Basics of Experimental Design for Cognitive Psychology. I am Dr. Ark Verma from the Department of Cognitive Science at IIT Kanpur. We are in week 5 of the course and we basically talked about different kinds of experimental designs, the one-way experiment design and the factorial design in the last 3 lectures. Now, moving on, something that is extremely important for experimental researchers is to be able to ensure that the experiments that we are carrying out, the measurements that we are carrying out are both reliable, we can sort of trust on them in the sense that the process has been followed and the measures are actually yielding what they are supposed to measure, and they are valid. So, both the reliability and validity of an instrument is extremely necessary, and it is from that perspective that I will be discussing about how to ensure higher reliability and validity of our experimental findings. In today's lecture, I will mainly talk about reliability. So, an important concern among researchers is to ensure that the measurements arising out of their experiments are reliable, basically meaning that there are no errors or no spurious measurements, and that the results can be conceptually valid, and the results are conceptually valid. Now, to ensure that these errors are minimal and that statistically and conceptually sound measures are used to interpret the results of the experiment, steps are taken to ensure reliability and validity. So, let us talk about reliability first. Now, one of the basic difficulties in determining the effectiveness of a measured variable is that this measure will always be influenced by some kind of error. Remember, we were talking about error and how do we minimize the possibility of error by increasing the number of measurements, and the idea is the more measurements we take, the amount of this random error reduces. So, that is basically the concept we are going to talk about today. What are the sources of these errors? These errors typically are clubbed under what is called a random error, and that random error can arise out of many sources. Let us look at that. So, it is possible that the measured variable contains some chance fluctuations in the measurement, which we call random error, which could arise from various sources, such as, for example, misreading or misunderstanding of the question, measurement of individuals on different places. Say, for example, you take a test in a particular classroom and then you take a test at a different classroom where temperature etc. are very different, the conditions are different, and the performance of the participant sort of varies. It is also possible, say for example, the experimenter has misprinted the question, or is in a behavioral experiment has misrecorded the responses of an experiment. You sometimes what students do is that they miscode, a line is missing, the responses are not getting recorded, or the responses are sort of adding some number, maybe an element of maybe 5 seconds, 10 seconds are getting added because of the response measurement devices and so on. So, there can be any number of sources that can bring random error into our measurements. Okay. Now, these random errors do influence the measured variable sometimes, but they do so in a way which is self cancelling. If there are any number of random variables that can have an effect on your dependent measure, a lot of times it will happen in a way that is self cancelling. What does that really imply? Basically, although the experimenter can make some recording errors or the individuals can give some incorrect responses, typically what you will find is that these errors will increase the scores of some people and decrease the scores of some other people. So, technically that is typically one of the reasons why people work with means and averages is that this will all balance each other out, and then the probability of the amount of error in your critical measurement will be reduced. In contrast, however, there is another kind of error that can be slightly problematic, is this error which is called the systematic error. Okay. So, the measured variable can also be influenced by other conceptual variables that are not part of the conceptual variable of interest. These are called extraneous variables or confounding variables, and sometimes we find that when we are conducting our experiments, these confounding variables have an influence in a very systematic way on the dependent measure that we are taking. Remember, we are thinking, or at least the expectation is that whatever measurement we are getting on the dependent measures is solely due to the manipulation in the independent variable. But if you have this kind of systematic error which is arising out of some other variables that are playing a part, then it decreases the reliability of the measurements that we are eventually getting. So, for example, let us take this example, individuals with high self-esteem may score systematically lower on an anxiety measure than those with low self-esteem, and more optimistic individuals can be expected to score consistently higher. So, that is something that you can actually see what what you are trying to do is you are basically trying to measure anxiety, and your anxiety is the dependent measure. If you have not taken care of self-esteem, if you are not already measured or controlled for it, then it can actually produce a systematic variance or a systematic error in the way your participants are responding to your scale. Also, sometimes what happens is that the participants that you call to your experiments will have a tendency to self promote. Participants are almost always trying to guess what the experiment is for. There is a certain degree of reactivity that you can expect from all participants across all kinds of studies. Okay. So, sometimes the participants have this tendency to self promote, and it can lead some respondents to answer the items in ways that make them appear less anxious, something that is that's a bit of an issue with most scales and most surveys, and especially when we do them with psychology undergraduates or postgraduate students, is that the students sort of have a sense of what the survey is for, and what they do is they will try and in some sense project what they want in the survey. So, for example, if you are doing an anxiety test and the person does not want to be portrayed as a highly anxious individual, they will themselves respond to the items in the questionnaire in a way such that they do not appear anxious. All right. So, a lot of times respondents will start answering your survey in a way that makes them appear less anxious than they actually are. They might be doing this for whatever reason, sometimes in order to please the experimenter or just to feel better about themselves. In such cases, what you will see is that the measured variable will basically be assessing self-esteem, optimism, or the tendency to self-promote, in addition to the conceptual variable of interest, that was anxiety. So, this is a very good example of how systematic error may sometimes creep in our measurements. In experiments also, for example, we were talking about that violent watching violent cartoon, prior state frustration and gender. A lot of times there could be other things that creep in. Remember, we were talking about the confounding variable of parents' disciplinary style. So, sometimes that may be playing an effect as well. So, this is basically the difference between random error and systematic error. You can see random error can arise out of various reasons: coding errors, participants' inattention, their misperception. Sometimes there are other things, maybe the condition, it is too hot and you are asking your participant to perform the experiment, they are tired very quickly, maybe in middle of a block, maybe in the beginning of a block, and so on. So, all of that can basically be as a threat to the reliability of the measurement that is happening, but it will eventually cancel each other out. Some participants will be very fatigued and tired when they come to your experiment, some will be extremely fresh. So, somewhere the score will go up, somewhere the score will go down, and eventually it will all cancel each other out. But in case of systematic error, when you have other conceptual variables in play, for example, self-esteem, mood, self-promotion. In the previous example, we can talk about, with reference to the previous example, we can talk about things like parents' disciplinary style. We can talk about other things as well, personality factors may come in. Okay. These basically are threats to the construct validity. They are sort of, they confound the actual measure that you are taking, and that is referred to as a threat to the construct validity of the experiment. What is it that you are trying to measure? If your item is not measuring that, but it is basically confounding with other conceptual variable, that is called a threat to conceptual threat to construct validity. We will talk about construct validity in more detail as we go forward. Now, we can see that the impact of random and systematic error on measured variable are slightly different from each other, and even though there is no proper way to determine whether the measured variables are free from random and systematic error, there are obviously techniques, statistical and methodological, that can allow us to get an idea about how well our measured variables actually capture the conceptual variable that they are designed to assess. In this case, we are interested in anxiety. Okay. So, let us see how we go about it. Now, the reliability is a very interesting concept. It basically refers to the extent to which the measurements are free from random error. Typically, when you want random error to be taken care of, you are looking at enhancing the reliability, you are looking at ways that basically allow you to first assess, then enhance the reliability of your measurements. Okay. A possible method to determine the reliability of a measured variable is very simply to measure it a larger number of times, measure it more than once. For example, one can test the reliability of a weighing scale simply by weighing the same object again and again and again and again, and say, for example, first time it gives you, let us say there is an object of 10 kg weight and you are putting it on the weighing scale. Suppose you are sort of calibrating the weighing scale, or it is a new one, you want to determine how this is working. First measurement, it gives you some measurement with some error, second measurement, it gives you some measurement with some other error. You do it 3-4 times and then you average it. You basically, what you have done is you have minimized the error component, it averages or cancels itself out, and then you get closer to the actual measurement. Okay. So, if your scale is giving the same measurement on several trials, then you can assume that it is a correct one, but it's in some measures it is telling 10, some measures it is telling 12, other measures it is telling 7, then you will also you can conclude that the weighing scale is not measuring the weight reliably. Okay. So, let us go forward and let us assess the different approaches to measuring reliability in an experiment. The first one and something that is very commonly used is called test retest reliability, the one that we were just talking about. So, test retest reliability is the extent to which scores on the same measured variable correlate with each other on two different measurements. So, you take some score measurement on day 1 and then on day 3 and then day 5 and so on, and when you compare the correlation between these, if the correlation is high, then you can assume that the measurements were reliable. If the correlation is low, then you can assume that the measurement was not as reliable. Okay. So, if the test is perfectly reliable and if the scores on the conceptual variable do not change considerably over the time period, the individuals typically, as experimenter, you should receive typically the exact same score each time, and the correlation between the scores will be tending to 1. See, 1 is the perfect correlation, 0 is no correlation at all. So, the idea is that whatever measure of correlation you will get, it will be approaching 1, it will be in the high, let us say 0.70 and above. Now, if your measured variable contains random error, the two scores will obviously not be highly correlated. So, higher positive correlations between the scores at the 2 times would indicate higher test retest reliability, and low correlations will basically indicate low test retest reliability. Now, although this test retest procedure is a direct way to measure reliability, it also has limits. Remember, we were talking about a bunch of things earlier, carryover, practice and fatigue, things like that. Now, for instance, when the procedure is used to assess, also it can we will just talk about this and I will come to it. For instance, when the procedure is used to assess the reliability of a self report measure, it can produce reactivity. So, this is what I was talking about. A lot of times when you are re-measuring the participant again and again, and it happens more with qualitative than with quantitative and experimental methods, but it happens that the participant starts responding slightly unnaturally to the procedure because they are trying to guess, or they have already guessed the purpose of the experiment. Okay. So, when you are doing let us say an attitude scale, or when you are doing a personality scale and things like that, and you are doing it again and again, what happens a lot of times is the participant is trying to double guess the experimenter. The participant will basically say that, okay, why is it, maybe the experimenter is expecting a certain kind of answer, maybe I did not provide it in the first instance, so let me change my answers in the next time and be more helpful, let us say helpful to the experimenter. So, this is, by the way, what is reactivity, and reactivity can actually be a potential problem, because when the same or the similar measures are given twice, the responses typically on the second administration may have been influenced by the measure already that was already taken the first time. These effects are typically known as retesting effects. So, if you do this again and again, and if you discover that the participants are changing their responses or unnaturally responding them, you know that there is a degree of carryover, practice, reactive reactivity based retest effects. So, retesting problems can actually occur in cases typically where people remember how they had answered or responded the first time to the same questionnaire. Some people believe that, some people, as I was saying, some people may believe that the experimenter wants them to express different opinions on the second occasion, and that is basically why they would just change their responses, and ideally it reduces the reliability of your measure. This pattern obviously would reduce the test retest correlation, because if you are responding, let us say, towards one end in the first administration, towards the other end in the second administration, obviously the correlations between these two values will be lower, or these two set of values across items will be lower. It could also be the case that the respondent might try to just duplicate the answer. Say for example, they want to come out as extremely consistent, so what they do is they remember what they answered in the first administration. Oh, I answered 1 here on a Likert scale kind of a thing. Between 1 to 5 you have to answer, so the participant remembers on each item what they opted for. So, on item 1 I said 1, item 2 I said 4, item 3 I said 2. If the participant remembers it and tries to exactly replicate the same in the second administration, then also it would unnaturally increase the reliability estimate. It will just be, if it is the same number across the two measurements, your reliability or correlation will actually increase to 0.9 or even higher, and that basically is also an unnatural inflation. You are basically not getting what you are looking for. Also, it can happen that participants get bored with answering the same question again and again, and that might also sort of be a source of differences. So, while some of the problems can actually be avoided using a long testing interval, so you do your first administration on day 1 and the second administration on day 30, or maybe day 15 and so on. Sometimes people will genuinely forget what they did in the first administration of the test, and they will still be natural on the second or the third administration of the same test, and in that sense it will not affect, it will not be a reactive response, it will not affect your reliability computations. Other occasions you can just use instructions, you can explain things very clearly and then hope that the participants are naturally and sincerely responding. Retesting typically becomes a general problem in the computation of, or retesting effects actually they pose a general problem for the computation of what is called the test retest reliability. So, to get around this, what people have done is, a lot of researchers often employ a more sophisticated type of test retest reliability known as equivalent forms reliability. So, what they do is, the items are not identical, but they are basically very similar and they are measuring the same thing. Okay. So, under this approach, two different but equivalent, say for example, you want to conduct a test about somebody's, let us say, language proficiency, English or something. Okay. Now, you have one test, and you on the next time you want to give another test, the items in these two tests are broadly measuring the same thing, they probably are organized in the same dimensional manner, but they are not the exact same items, alright. So, you can use two different but equivalent forms of the same measure, and you do that different times. So, then when you assess the correlations, you might be closer to getting the low random error and higher reliability estimates. So, this approach is this equivalent forms reliability approach is particularly useful when, say for example, certain items have correct answers to the test, and which basically can be learned by the individuals when they take the first test, or they find out during the time period between the tests that, oh, this is the correct answer of that item. So, ideally when you do not repeat the items, you have equivalent versions, it makes it much easier. So, and this is done in a lot of practical cases as well. Say for example, when students might remember the exact questions and learn the answers to aptitude tests such as the GREs and the SATs and the TOEFLs, our tests like the exams that are done in CAT, MAT and so on, typically these tests would employ equivalent forms. They are all trying to test the same thing, maybe on the second or the third administration, but the items are not identical there. Now, in addition to the problems that can occur when people complete the same measure more than once, there is another problem that can happen with test retest reliability, is that some conceptual variables actually will change over time within an individual. So, for example, it is also possible that it is not the the difference in responses is not because of the items, but it is actually because the conceptual variable that you are assessing or trying to assess, that has changed within an individual. Say for example, a lot of personality tests might be like that, that when you take a given personality test at the age of 15 and then 25 and then 35 and then 45 and 55, a lot of times the things that the personality test is trying to assess have actually changed. The conceptual variables, say for example, things like I do not know, optimism has changed, extraversion, introversion has changed, things like that. Okay. So, let's take that example, again something that Stanger has taken. If optimism has a meaning as conceptual variable, then people who are optimists on a Tuesday, again remember, we do not compare tests across a large period of time, typically you are trying to do first, second and third administrations within a short period. So, if you ask somebody to take a test on optimism or an optimism scale on Tuesday, you would expect them to be optimist also on Friday of the week. This is a characteristic that is assumed to be relatively stable in an individual, at least for short periods of time. Okay. These characteristics such as intelligence, friendliness, assertiveness, optimism for example, just as I was just saying, are known as traits which are personality traits, and they are not expected to vary across a very short period of time. Large period of times, yes, maybe. Okay. So, these are called traits, these are basically trait variables, and you would expect that they will not change very quickly over time. But then there are also state variables, for example anxiety, for example some kind of an emotional reaction, which can obviously change over a period of hours and over a period of days. So, other conceptual variables such as levels of stress, moods, or even say for example preference for classical over rock music, as I said, these are typically known as states, and these are personality variables which are expected to change even within the same person over short periods of time. As a result, what can happen is that a person's score on a mood measure which was administered on Tuesday is not necessarily going to be the same, it is not necessarily going to give the same information when the same measure is administered, let us say on the same Friday or the next Friday. In these cases, the retest approach will not really work to, and it will not really give us a good estimate of reliability. We will have to look for something else, we will have to look for a different approach. The other approach that people can take in order to assess reliability is known as the internal consistency approach. Now, what we are doing is, we are not hinging our bet on reliability on the individual, but we are basically trying to work on the internal consistency of the test or the measure. Okay. So, given these problems associated with the test, retest and equivalent forms reliability, a different measure of reliability known as the internal consistency has been the preferred choice and the most accurate way of assessing reliability for both trait and state measures. Internal consistency can be assessed using the scores on a single administration of the measure. So, you do not have to take the measurements again and again, and we have seen that most self-report measures typically contain a larger number of items. You will not have, typically you will not have a survey, or you will not have a test which has just one item, you will typically have them with many items. Okay. So, that is one of the ways that probably helps us to determine the internal consistency, and we will talk about that going forward. Now, when we are measuring something, when you are trying to take these measurements, there is something referred to as the true score and the random score. So, one of the basic principles in reliability is that the more measured variables are combined, when you average a lot of measurements over time, the more reliable the test will actually become. This is basically because although each measured variable will in some sense be influenced in part by random error, some part of each item will also measure what is called the true error, or let us say the true score that you are measuring, or part of the score that is not random error. Say for example, whenever you are collecting reaction times for something, and you are have this B of x in mind, which is the mental process that you want to sort of appropriate, obviously there will be some error. But when you do this over a period of time, when you have several measurements, what will happen is that these random errors will start cancelling each other out, and you will get closer to the B of x, you will get closer to the true score, which is basically what you are after. Also, and just repeating myself, I guess, as random error is self cancelling, the random error components of each measured variable will not be correlated with each other. So, anyways, they'll sort of not figure in the correlation. The parts of the measured variables that represent true score, they will actually be correlated. So, when you carry out correlations over a large number of measurements, the only thing that will start figuring out in correlation is basically the true score. So, consequently, when these several measures are combined together by taking an average or taking a sum of each of them, the use of many measured variables will produce a more reliable estimate of the conceptual variable than will any of the individual measured variables themselves. So, let us talk about how this is done. Now, typically the role of the true score and random score can be random score, which is basically the error component, can be expressed in the form of two equations that we are just discussing, and that forms the basis of reliability. So, just look at this: an individual score on any measure which you are sort of doing m of x will consist of both the true score and the random score, and the reliability that you want to really arrive at is basically the proportion of the actual score that reflects the true score. So, basically what you are trying to do is reliability will be true score divided by true score plus random score or actual score, and that is basically well equipped to give you a reliability estimate of how these measures are. Take an example: Rosenberg self-esteem scale has around 10 items, each of which are designed to assess the conceptual variable of self-esteem in each in slightly different ways. Now, although each of these items will have some part random error or will have some part of the random score, each will also measure some aspect of the true score, some aspect of self-esteem that you wanted to measure. Now, if you average, or if one averages all 10 of these items together to form a single score, single measure, ideally what should be expected is that the overall scale score will be more a more reliable measure than will be any of the individual items. So, typically that is why you will see that a combined score or an average score is taken on these scales, which give you a combination and which tells you more about the conceptual variable that you are interested in as compared to a single item. Now, internal consistency in this case refers to the extent to which the scores on the items correlate with each other and thus are all measuring the same true score rather than being affected much by the random score or the random error. Now, regarding this scale, a person who answers, let us say, above average on question number 1, let us say that is measuring one aspect of self-esteem, indicating that he or she has a high self-esteem, should also answer above average on all the other questions, because they are also measuring self-esteem. In that sense, these responses among these different items can be or must be expected to be correlated. So, this pattern obviously will not be perfect, it will not be always 1.00 all the time, but because each item will have some error as well, but to the extent that each of the items are measuring the same conceptual variable, they are assessing the same true score rather than being affected too much by the random error, the average correlation among the items will be approaching R is equals to 1.00, the perfect correlation. And to the extent that the correlation among items is less, let us say it is closer to 0, it tells us that there is too much random error or that the items are not really measuring the same thing. Okay. There is a typo here. Now, one of the ways to do this is the coefficient alpha approach as well. So, one of the ways to calculate the internal consistency of the scale is to correlate a person's score on one half of the items with the person's score on the other half of the item. Say for example, you have a scale having 100 items, what you could do is you compare the correlation of the first half 1 to 50 with the correlation on and you correlate this with the score on the 51 to 100 items. So, you basically do that. You can also randomly pick, let us say 1, 3, 5, 7, 9, and you have on the other half 2, 4, 6, 8, 10, and you basically correlate their scores on each of these two halves. This procedure is known as split half reliability. Okay. If the scale is reliable and if it is not too much affected by a random error, then the correlation between the two halves will approach r is equals to 1, indicating that both halves of the scale are measuring one and the same thing, and they are both halves, all the items across the both halves are appropriating the same true score. Now, since split half reliability uses only some of the available correlations among items, it is preferable to have a measure that indexes the average correlation among all of the items on that scale. So, it is a slightly different way of doing it. Now, the most common and the best index of internal consistency that is typically and widely used is called the Cronbach's coefficient alpha. This measure is an estimate of the average correlation among all of the items on the scale and is numerically equivalent to the average of all possible split half reliability. So, this is again something that is a statistical measure to allow you the best estimate of split half reliability given your scale. So, coefficient alpha, as it reflects the underlying correlational structure of the scale, ranges from 0.00 indicating that the measure is totally just error to plus 1.00 indicating that the measure has no error at all. Again, I am sure it is clear that perfect correlations will be very rare to be found. There is also another way to sort of have this internal consistency in hand, which is the item to total correlation. So, you basically take out a comparison between one item and the rest of the scale. Let us talk about this. When a new scale is being developed, its initial reliability may obviously be low, and this would be because that even though the researcher has selected the items that he or she believes will be reliable, some items will turn out to be containing more random error for reasons that sometimes researchers will just miss while planning and creating these items. So, a strategy commonly used in the initial development of the scale is to calculate the correlations between the score on each of the individual items and the total scale score excluding the item itself. So, for example, I have a scale of 10 items, I have the score of item number 4 separately and the other 9 items separately, and I compare their correlation. I calculate the correlation between them. This is known as the item to total correlation, which is also an interesting method, which is also a useful method to assess the internal consistency of your scale to give you, for example, the best reliability estimate possible. So, the items that do not correlate highly with the overall rest of the scale or overall total score can then be deleted out from that scale. Now, as this approach basically deletes the items that are not high in correlation, it will lead you to reduction in items. So, typically what happens is, and you will see that a lot, people create the initial scale with 20, 50, 100 items, but after these calculations, after you have run these tests a few times and you have computed these correlations, a lot of items get deleted. So, what you have is a much shorter scale, smaller scale, but with a higher estimate of reliability, and you can trust it more and you can use it more widely. Another sort of approach that we have not talked about so far is that a lot of times individuals are also not, individuals, the raters are also afflicted with some kinds of errors. So, reliability is not only important in terms of these self-report scales, but they are also important in terms of behavioral measures that we collect from these participants, and therefore, it is a common practice, let us say it is a common practice for a number of judges to rate the same observed behaviors, and then we take an average or we combine their ratings to create a single measured variable. Okay. So, there are item level reliability estimates as well, and you have to have inter-rater reliability also, so that you have a broad sense of how the raters are answering on a particular item or whatever measure you are interested in. These calculations require the internal consistency approach as well. So, for example, just as any single item on the scale is expected to have error, the ratings of one judge or an individual judge is also slightly more likely to contain error than the average rating across a group of judges. Okay. The errors of the judges can be caused by several things, including, say, for example, inattention, time of the day, misunderstanding of instructions, or even personal preferences. When the internal consistency of a group of judges is calculated, the resulting reliability estimate is known as inter-rater reliability. Previously, we were talking about items and how to enhance and magnify the reliability of the items on a scale. We can also do that at the level of the raters as well. Now, if the ratings of the judges that are combined are quantitative variables, then coefficient alpha can be also used to evaluate reliability. However, in some cases the kind of measurement you are taking is nominal measurement. So, it is basically say for example, in a scale where you are asking judges how did the children play, did they play aggressively, did they play cooperatively, did they play alone, that kind of thing will not give you easy numbers. So, in such cases a different statistic is known, which is the kappa statistic, and it is used as a measure of agreement among the judges. Okay. So, how did these judges sort of feel about this given behavioral measure? So, like coefficient alpha, kappa also ranges from 0.00, which basically indicates that the judges ratings are entirely made of random error, to plus 1.00, indicating that the ratings are almost perfect. Okay. So, this is broadly all about reliability that I wanted to talk about. In the next lecture, we will talk about how to fight systematic error, and we will talk about various ways of addressing construct validity. Thank you.